Hello everyone, my name is Rolf Svenning. I'll be presenting the paper External Memory Fully Persistent Search Trees, which is joint work with Gerth, Stølting, Brodal and Casper, Moldrup, Rysgaard. As the title suggests, in this paper our contribution is an improvement to External Memory Fully Persistent Search Trees, where we improve on the previous best result by Brodal, Ceutas, Sakalidis and Ziegler from 2012, and we do so by shaving off this additive log-based 2FB term in the update time. This is an overview of what I'll be talking about. So there's first some preliminaries. And first of all, this is a result in external memory. And external memory is this model where you have an internal and external memory, and you're trying to minimize or optimize over the amount of data that's transferred between internal and external memory. Then it's a result in search trees, and in particular persistent search trees. And in general, if you have a data structure, if you have a normal data structure, usually updates are so-called destructive. And what I mean by destructive is that you have one version of your data structure, then you apply an update. This derives a new version of the data structure, but the update is actually destructive in the sense that you lose access to the earlier version. So you can kind of think of updates as deriving a history of your data structure, a bunch of earlier versions of it. And then when you're looking at persistent data structures, it's because you actually care about these earlier versions. And among other things, you want to allow queries in any earlier version of the structure. Then I'll talk a bit about how we got there, how we got this result. First of all, we exploit a known correspondence between persistence and geometry as a way to interpret persistence in a geometric way. And then the natural way, what we do to improve is to actually fully embrace this geometric view and design a structure where all updates and queries fully take place in this geometric setting. So first of all, we have the external memory model. It's this model where we have an external memory of infinite size and an internal memory of size m, and all computation takes place in internal memory. Both internal and external memory are divided up into blocks of b consecutive elements, and what the algorithm can do is it can transfer blocks back and forth between external and internal memory using so-called IOs. The standard setup, or a standard setup, is that you, for example, for an input of size n, it's initially stored in n over b consecutive blocks in external memory, and then as the algorithm tries to compute something, it will move parts of the input into internal memory, do some computation, write something back, and so forth. And the complexity measure in the model is then the number of IOs that are performed, and the space usage is how many blocks of external memory do you use. Standard bounds in this model is, for example, scanning. If you want to scan in items, for example, compute some aggregate, you can do so using n over b IOs. And another standard bound is, for example, sorting, which is this term here. And for example, one intuitive way to understand why you could get a base of m over b in the logarithm is if you perform a m over b way merge sort, where you can concurrently merge m over b different sorted runs by keeping the first block of each run in internal memory. Next up, we have something familiar, which is search trees. So what we think of as search trees in this paper is just a data structure which for some totally ordered set S supports the following four operations. These are insertions and deletions of elements. It's the search for an element, which is actually a predecessor search for the element X. And then a range query, which just asks to report all the elements in S between X and Y. And in internal memory, this is well understood to be solved by, for example, balanced binary search trees, such as red-black trees. And here, operations can be performed in time proportional to the height of the tree, so log base 2 of the size of S. And this plus k here, just where k denotes the size of the output, is just to allow the operations also, of course, to take time to actually execute or perform the output. Okay, and the space is linear. Then in external memory, the classical solution is the B tree by Bayer and McCrae from 1972. And this is very similar to a binary tree. Instead, you have a tree where nodes have degree roughly b. So instead, you get a base of b in the logarithm here. And for the output term, you have a division by b, so you're not allowed to spend one block or one IO to output a single element. You want to output b elements at a time, basically. And similarly, linear space in the external memory model would be size of S divided by b. Then we have persistent data structures. So as I mentioned, if you have a normal data structure, we call this an ephemeral data structure. And here we have, it starts in some version, you apply updates, you get new versions, but updates are destructive, so in fact it's only the most recent version of the data structure that is available for both queries and updates. Partial persistence is then the natural extension of this, where you can now actually query any earlier version. You maintain sort of a history of the past, but you're still only allowed to update the most recent version. And to actually derive a new version, we introduce a new operation, or a specific operation for this that we just call clone, which returns a copy of some version. But since you can only clone also the most recent version, this version history here will form a path for partial persistence. If you instead look at full persistence, the only change basically is that now earlier versions can also be cloned. And you can kind of think of this like Git. You can go back to an earlier version, and then you can clone it, which corresponds to a fork, and in this way your version history will instead form a tree. And updates are still only allowed to be performed at the leaves. It would be, if you could, for example, perform an update at some version that already has descendants, well, the update to this version would somehow have to also propagate to all the descendants, and this is also not allowed for full persistence. Okay. And in an important paper by Rysgaard, Slater, and Sargent from 1986, they introduced several techniques to make linked data structures persistent. And all of these techniques are based on the crucial notion of timestamps. So here we have an example of a linked data structure. So for example, let's say of a search tree, and we can see on this edge and on this edge we have these timestamps here. And what the timestamps do is they indicate that this edge should be considered from version 1 and forward, modeled by infinity here. And the trick is now that when you perform a deletion, you don't delete the edge of your data structure. That would be a destructive update. So instead what you do to delete the edge, you simply put an end timestamp indicating that this edge should only be considered from version 1 to but excluding version 2. Okay. And now similarly, if you perform an insertion, maybe the same edge gets inserted again. We use this timestamp here to indicate that this edge should actually not be considered in these two versions. It should only be considered from version 3 and forward. Okay. So this is a way to make updates that are non-destructive and allow for these persistent queries in earlier versions. And this example here is actually an example that only is kind of valid for partial persistence, where versions have a nice natural order from, let's say, left to right in time. For full persistence, the story is a little bit more tricky. If you, for example, consider an insertion in version 4 that it gets deleted in version 9, well, this interval here, or this element here, should not be considered over here in version 6, even though version 6 lies in between 4 and 9. So, and of course because it's on a different branch. And the problem is basically that for full persistence there's no nice ordering of versions. Versions are only partially ordered. But nevertheless, also in this paper they introduce a so-called node splitting technique for full persistence. And in fact, you can still use timestamps to get full persistence. You just need to be a little bit more clever about it, because it's not as obvious which order of how you should order the versions. But using an order maintaining structure by Dietz and Slater, you can still make enough sense of how versions are ordered to get this idea of timestamps to work for full persistence. And it's an important caveat that they use this order maintaining structure when thinking about external memory, because in fact making these order queries takes constant number of IOs for a single query, which is not efficient enough to improve in external memory at least. Okay. So what are some of the previous results or related results for this problem? Well, we have the classical B trees here by Bayer and McCrate. And then we can see for partial persistence, we actually have bounds that are matching those of classical B trees. And here we have a result by Au, Danner, and Ter from 2003. Yeah. And N subscript B here just indicates that the operation takes time proportional to the size of the version you're accessing. So N subscript B here is the size of version B. Okay. And this is of course important. You want that if you make an operation in a small version, it should be faster than if you make an operation in a big version. Then for full persistence, we have these two results by Lanka-Mays and by Brodal, Siotas, Zakalides, and Siglas. And we can see neither of these bounds are matching the classical B trees, and this is our contribution. We get bounds that are matching the classical B trees. And we can see compared to, for example, this result here, we're shaving off this additive log base 2 of B factor. And also, I should mention that this result here, actually, what they do here is actually to employ this node splitting idea and move it to external memory. And they use this order maintaining structure, and the usage of this order maintaining structure is exactly why they get this additive log base 2 of B. And it was clear to us when we were working on improving that resorting to using this order maintaining structure would, we couldn't do that. It would always introduce this additive log base 2 of B. Okay. The story is not quite over now, because in 2003 Brodal and Ferber introduced the B epsilon tree, and they perform updates significantly faster than classical B trees. So here epsilon is a tuning parameter that can be taken to be any value between 0 and 1. So this is natural open problems. Is it possible to actually combine this idea of buffers, which they employ here for updates, with persistence also? So both of these results are only matching the classical B trees. We're not matching the optimal B trees in external memory. And as I mentioned, there's a nice sort of correspondence between persistence and geometry. I'll try and explain how that works. So here we have a version tree. You can see the nodes correspond to versions, and next to the nodes there's the updates that took place in that version. So for example, we can see we have version here, and some updates were applied, and then it was cloned to version 2, an update was applied, cloned to version 3, an update was applied, cloned, an update was applied. And if we look at version 4, which values are contained in version 4? Well, 2, 5, and 6 are contained because 7 is inserted here, but it's deleted here later, so it's cancelled. So how does this geometric interpretation look? Well, you get a bunch of segments, vertical segments in the plane. And on one axis you have all the elements ordered by their value, and on the other axis you have the version list. Crucially, this ordering is less obvious. So this ordering here is in fact a pre-order, corresponds to a pre-order traversal of the version tree. And this was also described in this paper by Driscoll, Sarnak, Slater, and Sargent. And the way to now interpret this geometric view is, if you for example consider version 4, which versions are contained? Well, you shoot out you consider a vertical or a horizontal segment from version 4. You look at all its intersections with vertical segments, and node segments are including in one and excluding in the other. So it's intersecting this segment here from value 2, this segment from value 5, and this segment from value 6, indicating that version 4 contains values 2, 5, and 6, which was consistent with what we had over here. And now query is sort of obvious how to do. So for range queries, it corresponds to a segment. So this is a range query in version 6 from value 3 to 8. So you of course look at the segment spanning exactly this region here. And now you look at all the vertical segments that it intersects, and that is what you should report in the range query. Similarly, for a search or a predecessor query, in for example version 7 at value 9, well, you look to the left and you look at the first segment that is intersected. This is a 6, value 6, so that is what should be reported. And what I didn't explain is how our updates actually performed, how our segments in fact inserted into this geometric view. And luckily this is also actually quite straightforward. So for example, on a clone of version 1, well, to clone version 1, you simply, in the version list, insert the new version immediately after 1 in the version list. And you can see in this way, this new version will automatically contain everything that the version it was cloned from also contained. Then if you have a deletion, for example in version 7 at value 7, you find version 7 at value 7, and then you delete the unit interval spanning from version 7 until its successor in the version list. And this, for example, here has the effect of breaking one segment up into 2 segments. But it's a small change, you just have to delete a unit segment in the plane. Similarly for an insertion, well, you just insert the corresponding unit segment at version 6 at value 4, the unit segment to its successor in the version list. And now we're sort of ready to understand what we did. The natural thing is, of course, let's just maintain this geometric view and be able to perform all these queries and updates completely in the geometric setting. So we take this plane here, which had all these segments, and then we divide it up into all these rectangles. So we have a small rectangle up here, a larger rectangle up here, and so forth. And all segments are stored inside these rectangles. And these rectangles have to satisfy certain invariants. So the first invariant here is that the number of segments in each rectangle should be order r. And r here is a parameter which we set to be b log base b of n bar. And n bar here is a bound on the total number of updates that are applied to the structure. What we actually want is to have this be proportional to the size of the version we're accessing, but we'll see later that you can actually change one for the other. So for now, just think of it as being either one. Yeah, but basically what this first invariant guarantees is that you actually have time to scan all the segments in a single rectangle and still hope to obtain the reporting and update time we're looking for. So scanning takes time proportional to r divided by b. Okay, so that's why we have the first invariant. The second invariant is needed for range queries. So for example, here we have a range query, and this invariant here says that the number of spanning segments in a rectangle should be at least a constant times r. And a spanning segment is simply a segment that spans from the bottom of a rectangle all the way to the top. And the reason why we have this invariant is that if you consider, okay, for a range query you have a leftmost rectangle and a rightmost rectangle, and then you have a bunch of middle rectangles. But for all the middle rectangles, you're actually guaranteed to report all the spanning segments. And now, since the spanning segments are a constant time, at least a constant times all the segments that are inside the rectangle, then we are outputting enough that the time we spend on dealing, like the total time we spend on dealing with this rectangle, we can actually charge this to this output term here. Okay. So we output enough from all the middle segments that we can just charge it to the output. So that's the reason for this second invariant here. And there are some more invariants also, but these are two crucial ones. It's probably the first ones you come up with. And of course, you have to also talk about rebalancing. So this is a dynamic problem. Updates will cause these invariants to break. And at the sort of one level up, at the rectangle level, we perform some rebalancing operations of rectangles to maintain these invariants. And these primitive rebalancing operations are vertical splits and joins and horizontal splits. These rebalancing operations are then combined into more complicated rebalancing operations such as a merge. A merge is, for example, needed in the case where we have a rectangle R here, where deletions cause us to cause a violation of this second invariant here, that there are no longer enough spanning segments in here. And we fix it by making all these vertical splits or horizontal splits and then vertical joins, such that the spanning segments from this right neighbor here gets joined with this new smaller rectangle here, which yields this rectangle. Okay. And in fact, there are a bunch of, or a couple more complicated merge cases, and this is probably the most technical part of the paper. But what we found, or what we find using an amortized analysis, is that these rebalancing operations are actually rare, and the total number of rebalancing operations is only n over r. Okay. Yeah, and then in the amortized sense, when these rebalancing operations also happen, they can actually pay for themselves. Next up, we need to navigate this geometric view, and we have imposed all these rectangles, or we have created all these rectangles. Now, for example, for a range grid like this, we need to find this first rectangle here. And this is again something that takes place like one level up. It takes place on this rectangle view, or this rectangle level of view. To find this rectangle, we model it as a point location problem, which as always, or typically, not always, which as often is modeled as a ray-shooting problem towards the bottom segment of each rectangle. Okay. So for this query here, we hope to discover this bottom segment here. And the first idea is, well, let's just use an existing external memory point location data structure. And here are two of the state-of-the-art point location data structures by Monroe and Neckridge and R. Brodal and Rao. But unfortunately, they're not fast enough since we're hoping for operations that takes time roughly, or takes time order log-based BFM at most. Okay, so both of these other point location structures are simply not fast enough with queries. Okay. Another reason why it's not obvious that we can actually use existing structures is that in our setting, even though it looks like a nice geometric problem, it's a little bit of a weird geometric problem because one of the axes is not nicely ordered. It's ordered by this pre-order traversal of the version tree, all the versions here. But nevertheless, we devise a sort of special point location structure for our setting with very fast queries, and we get here by, first of all, trading fast queries for very slow updates and a superlinear space usage. And furthermore, it's also specialized in the way that our problem is an orthogonal problem, and in fact, it suffices to only consider insertions. And the reason for this is if you look at how the primitive rectangle operations behave, then the total area covered by all the bottom segments of all the rectangle, this area only increases. Okay. But we devised this fast point location structure that we can use for our setting. And we do so using standard techniques, which is weight balance segment tree plus fractional cascading. Next, there's a less obvious problem that we need to solve. So on the higher level, we use point location, and we, for example, for this query, we find this purple rectangle here. Within each rectangle, all the versions, for all the versions inside a rectangle, we maintain a local version or a local ordering of all these internal versions. And we do so such that as soon as we enter a rectangle, we can actually start comparing versions and segments efficiently. Okay. The problem is that even though all the local versions inside the rectangle they know where they are in the local ordering, when you enter the rectangle, you do so with a version from the outside, from the global view, and if this version is not represented already inside the rectangle, it doesn't know where it is in the local ordering. So to figure that out, we use what we call a colored predecessor structure, and what this does is it performs a predecessor query for some version, and then it finds the predecessor only among, for example, the purple versions. And as soon as it finds its predecessor, well, then we also know where this global version belongs in the local ordering. In the local ordering inside this rectangle. And just as an example, consider, for example, a global version list consisting of all the black versions here. And then with every rectangle, we associate a color, and we get a bunch of colored copies of versions. What we then do is we line up all these colored copies together with their corresponding global version. And now a colored predecessor query, for example, for the purple predecessor of version 5, well, we have version 5 here. We skip version 3 because there's no purple copies. We skip version 2, we skip version 6, and we find, okay, version 8 is our predecessor in this rectangle. Now we know where version 5 belongs in this local ordering. Finally, how do we get from this in bar, this upper bound on how many updates take place are allowed in the structure, to this n subscript v, the size of the version we're accessing, which is what we actually care about. And we do so by making certain cuts in the version list, such that within each slab, all versions have roughly the same size, roughly size proportional to this upper bound And this upper bound here, we actually set this to be 1 plus c times n0, where c is a small constant between 0 and 1. And n0 here is the initial size of this bottommost version in the plane. Or equivalently, it's the initial n0 insertions that happen in the bottommost version here before any other updates takes place. Okay. Now, since only c times n0 additional updates take place, then in fact all versions in the plane here will be of size within a constant factor of this n0 here. And thus all versions are within a constant factor in size of each other, and also within a constant factor of this upper bound here. And now anywhere where we have this parameter here appearing in other places in the structure, well, we can just replace it by the size of any version, because any version is anyways roughly of same size. Okay. And now, when do we make these cuts in the version list? Well, we make a cut as soon as we, of course, hit this bound on how many updates we allow. Next, where do we make this cut? So this is a little bit more tricky. But what we do is we actually look at the version tree, and then we find some version here which in its subtree contains a lot of updates. And that corresponds to being a lot of updates in the slab. And then we cut out this part of the version tree. And this is slightly simplified, but we cut out this part of the version tree such that we get 2 independent version trees. And then we rebuild both of these, all the structures associated with each of these version trees completely from the beginning. And each of these independent structures will have their own n0, their own initial size of the root. It's in fact the root, that's the bottommost version. And since there's always a linear number of updates taking place before we make one of these cuts, then we can actually afford to rebuild all of these new independent structures when we get them in the amortized sense. Yeah, and this brings us to the main result, which is that there in fact exist external memory fully persistent search trees with bounds matching the classical B trees. And the natural open problem is, of course, as I mentioned, can we actually make updates more efficient as was done for these B epsilon trees by Brodal and Faber in 2003 by introducing these notion of buffered updates. And partial results here would be to buffer the point location structure or the colored predecessor structure. Thank you very much all for listening. I put some references here if you want to check out some of the papers that I mentioned.